this video is only for those of you who are going to have to go on into college algebra. If that's the pathway in mathematics that you have to go to, you need to learn the skills on this video. And I'm actually sending you a worksheet that matches this. So you will do worksheet 2 instead of worksheet 1 because it's going to demand that you do this on this worksheet. So we have already looked at doing radicals with a calculator to get an approximation that you can visualize, because in Pythagorean theorem, that's what you need to do. And you will also do those Pythagorean theorem papers. But you also need to know how to simplify radicals with exact numbers. So this is what we're going to look at in this video, is how do you simplify radicals with exact numbers. And I'm also going to introduce you to the idea of imaginary numbers, because you will need those for the next level. As you remember, you've already watched the video where we had things like the square root of 16 is equal to 4, because 16 is 4 times 4, and the square root is asking you what is the number times itself that will equal 16, and that's 4. But now we're going to look at ones that do not do that, and these are called irrational numbers. And yes, you can get that on the calculator as 7.07 rounded to the 100th place value. But that's not what we're going to do. Right now you're going to take this number and you're going to get an exact simplification. And to simplify these, the first step is to look at 50. And is there a perfect square as a factor of 50? And there is. There's 2 times 25. 25 is a perfect square. So we can rewrite the 50 as 2 times 25. And then, because we have a rule in math that says I can have the square root of a times b is equal to the square root of a times the square root of b, we can simplify this as the square root of 2 times the square root of 25. And you know the square root of 25 is equal to 5, so this is equal to 5 times the square root of 2. I changed the order, and that's possible. You can always change your order. And so this produces a whole number, which is your 5, and it still multiplies the radical 2, which is irrational and does not simplify. Now, why can we say this? Well, let's look at this. If I have the square root of 9 times 4, this would be equal to the square root of 9 times the square root of 4. Let's see if that's true. The square root of 9 times 4, this would be the square root of 36, and the square root of 36 is equal to 6. Square root of 9 is 3, square root of 4 is 2, and 3 times 2 is 6. So we can show that that is true. So it's really important. If it's multiplication or if it is division, we can split them up that way. So now let's look at some other examples. This one was nice because you knew most of you know that 2 times 25 is 50. So that one's not a hard one to do. How about the square root of 18? Well, again, 18 is 2 times 9. And therefore, this is the square root of 9 times the square root of 2, because I can take these two factors, put each one under their own square root. The square root of 9 is 3, because 3 times 3 is 9, and the square root of 2 does not simplify. It is irrational, and you end up with 3 square root of 2. But what if we have numbers that we really don't know if they have any perfect squares or not? How would we do those? So let's do one like that. How about 56? Okay, what are some numbers that equal 56? Well, let's go. I know that 7 times 8 equals 56, and 8 equals 2 times 4, And this one is a perfect square, or I can factor it down to 2 times 2. Now remember, 2 of them the same is what is going to make it come out of the house. Here I have 2 the same, so that can come out of the house as a 2. And then I have 2 of them here that are leftovers and 1, so 7 times 2 is 14. Thus, since 14 does not have a perfect square in either one of these, there's no 2 of them, it becomes what goes inside the house. So this is another way to do it when you don't know for sure what you've got. So it's a really good way. Let's look at another one. How about the square root of 115? Well, 5, it ends in 5, so this would be 5 times 2, 3. Oh, well, there's nothing. Square root of 115 is as simple as it goes. It won't simplify down anymore. So let's try another number. How about 145? Square root of 145. So this is 5 times 45, 9. Again, that won't work. 29 is prime, 5 is not prime. Let's try another one. How about square root of 150? This is 10 times 15. This is 2 times 5. And 15 is 3 times 5. Notice I have 2 of a kind here. So that's going to bring my 5 outside the house, leaving me a 2 times a 3, which is going to give me my square root of 6 inside my house. Okay? So this is simplifying your basic radicals, getting it simplified in an exact number that equals what you started with. If you do it on a calculator, it's an approximation or an estimation, and you need to be able to do this. Now let's look at some that have a number outside that multiplies that. So let's go 4 times square root of 75. Well, 75 is 3 times 25. This is 5 times 5. So we know we have to bring our 4 over because it's multiplying what we've done inside my radical. And so here's my 2 of a kind, so my 5 comes out of my house, leaving me with this 3 inside the house. This one's done because of this. And now 4 times 5 is equal to 20. So this becomes 20 square root of 3. Okay. You're also going to have to look at like terms. So we can add and subtract these with like terms. So let's look at them. How about 6 times the square root of 2 plus 4 times the square root of 2? Square root of 2 and square root of 2 are like terms. Therefore, 6 plus 4 gives me 10 square root of 2. I can also do the same thing with subtraction. 6 square root of 2 minus 4 square root of 2 is equal to 6 minus 4 leaves me 2 square roots of 2. So these are ones that are the same. They're like terms. How about this one? I have square root of 45 plus square root of 125. And you're going to look at that and say, but those aren't like terms. But remember, we can simplify these. So when we simplify them first, maybe we will have like terms. So this is 5 times 9, and 9 is 3 times 3, giving me 3 on the outside with the square root of 5 on the inside. Simplified. This becomes this with simplification. Plus, and this one is 5 times 25, and therefore this is 5 times 5. There's my 2 of a kind, becomes outside, leaving me with my square root of 5 inside, just like that one. Now as you notice, these are like terms, and 3 plus 5 is 8 square root of 5. So you can add and subtract these, you can simplify them, and then add and subtract. The number under our square root is called the radicand. Now, sometimes the radicand is negative, and for the students that are going on into college algebra, you need to understand what happens when you have a negative radicand. In other words, it is going to look like this. See, my negative is underneath, and that creates a problem because 3 times 3 is equal to a positive 9. Negative 3 times negative 3 is equal also to a positive 9. So 2 real numbers, or 2 whole numbers, or integers, neither one of these that are the same will give me a negative 9. Therefore, that negative 9 is not a real number, and we call this an imaginary number. And we talked about how mathematicians like to grow and expand their learning. And one day mathematicians sat down and they said, you know, it would really be nice if we could do the square root of negative numbers, but we know it's not real, so we're going to make up our mind to do an imaginary. So what they decided is that they would make the square root of negative 1 is equal to the letter I. And that stands for the word imaginary. So we can now take the square root of negative 9 and break it into the square root of 9 times negative 1, which is equal to the square root of 9 times the square root of negative 1. Now, we know the square root of 9 is 3, so this is equal to 3. The square root of negative 1, by definition, is the letter I. And so the square root of negative 9 is equal to 3i. Okay? You got that? Now, what happens when we use ones that are not exact? How about the square root of negative 50? Again, this is going to equal the square root of negative 1 times 2 times 25, because I want to break up 50 into 2 times 25, all times a negative 1. This is going to give you a square root of a negative 1 times a square root of 2 times the square root of 25. Now, the order we write these in is not important. So what we're going to end up with, that negative 1, square root of negative 1 is I. Square root of 25 is 5, leaving me with the square root of 2, which is irrational. And so therefore we end up with 5i times the square root of 2. And this is interesting because notice where I put the I. Over here I put the I at the end, which is a normal way to do it. On this one I put it between my 5 and my radical 2. And the reason I did that instead of writing it this way is because a lot of times when you write it this way, this I slips back underneath the radical sign. And it cannot do that. That's not a permitted thing to have happen. You can't have the square root of a I, okay, of an imaginary number. It's not permitted in mathematics. Because it's already imaginary, you can't take the square root of an imaginary. And so therefore, 5i square root of 2, it doesn't have a chance to go underneath. If you want to write it this way, put your I inside parentheses, and it will not go underneath your square root symbol. So be careful on those. Either direction will be good to go. Okay? So what would happen if we tried to add or subtract these imaginary numbers. So let's look at some of those. Square root of negative 36 plus square root of negative 4. Okay? Well, the square root of negative 36 is a 6i because this is your I. Square root of 36 is 6. Plus, again, the negative is your I, and the square root of 4 is 2. So 6i plus 2i equals 8i. And now, let's look at maybe subtracting that. What if we had the square root of a negative, let's go 49, minus the square root of a negative 16. Again, that's your I. Square root of 49 is 7 because 7 times 7 is 49. There's your I with your negative sign inside, and square root of 16 is 4. So 7i minus 4i is equal to 3i. And these work just like the radicals when you're combining like terms. So let's look at a few of those. Okay, these are all like terms. 6i plus 8i is 14i minus 2i is 12i. Okay, add and subtract them just like you would like terms. Now, we're going to also look at a complex number. A complex number is made up of a real part and an imaginary part. Made up of a real part and an imaginary part. Okay. These are, we went through the real number system already, the first couple lessons, the first lesson. Well, this is the other side of it, and in fact, it is a larger number system than the real numbers because the real numbers are inside the complex numbers. So if I were to draw a picture of this, it would be like this. Complex numbers, and it's made up of real numbers, which you've already studied, and imaginary numbers. Okay, complex numbers contains both of them. So if I have my real part plus my imaginary part, and it's written as A plus BI. There's your I for your imaginary, B represents a real number, and A represents a real number. So if we have 6 plus 0i, 0 times I is 0, so this is equal to 6. So in my complex numbers, I can have my real numbers because I can express all my real numbers as an imaginary number. I can also express all my imaginary numbers as a real number, as an imaginary number, because 0 is my real number part, so 0 plus 6i is just simply 6i. So that's why you have your real number part, your imaginary part. So now let's look at adding these. There's one complex number plus, I'm going to put them in parentheses just so you can see the complex number. Okay, now we don't need the parentheses to do this when we have a plus here, because these are just exactly what they are. So I add my real part to my real part, which is 11, plus my imaginary part and my imaginary part, which is going to be 2i, because 4i minus 2i gives you 2i. So let's do one that's subtraction now. 8 plus 4i minus 3 minus 2i. And now we're going to have to treat this first as a multiplication, as though I have an invisible negative 1 giving me 8 plus 4i minus 3 plus 2i, because negative 1 times negative 2i gives me a positive 2i. Now combine my like terms. 8 minus 3 is 5 plus 4i plus 2i gives me 6i. So you can add and subtract these complex numbers as well. All right? So this video is for those of you who are going to college algebra only, because you need this information before you get there, and you need to know it. And 112 and 113 doesn't cover this very well. So you need this foundation for those courses. So this is for you, okay? Awesome and wonderful. I'll have a different worksheet for you as well.